Greetings! Welcome back to the Old Ways Rising Farm YouTube channel, where we are deep into our little journey in metal casting. Now, you've recently seen videos where we've made the flasks. We're going to move into videos where we make the pattern board and start to actually make and assemble molds and go forth with the project proper. But here, I need to do this little video as an interlude to explain a few things that you need to know when making molds. A mold is more than just a pattern with sand packed around it. That would be utterly useless. How would you get the metal and what would it do once it got there, and how would it shrink up if you managed to accomplish that somehow, right? So to make a not useless mold, we need to consider a few other factors. So I wanted to do this brief whiteboard talk, explain a couple of terms, explain a couple of extra things that you need to consider when making your molds. And every time I see people make molds on some of the more sensational metal adjacent television shows and lots of things on YouTube channels, it's really cringy because they're not doing these things. And when they don't do these things, they have bad results. Okay? On really, really small projects, you can get away with more, but the larger and more complex project, the more you absolutely have to mind these rules. So, please, I hope that you'll take a couple of minutes out of your day just to follow along. I'll give you the rules. I'm going to give you some rules of thumb to think about. It's not real technical. It's a little technical, but it's not real technical. And knowing this background will help you design better molds and get better castings when it comes time to do your own metalwork projects. So let's dig into the information. So first, the quick terms. Pattern. This is obvious. This is your widget or your thingamabobber. Right? This is what you're trying to mold. If you didn't already have a pattern, you wouldn't be looking at making a mold. So, done with that. Gates and sprue. This is how your metal gets to your pattern. So the sprue is the vertical hole, and the gates are the channels between the bottom of the sprue and the cavity left by your pattern. Okay? Again, fairly self-explanatory. This isn't the part that trips people up. The risers are. And the risers end up being complicated, because what the risers are reservoirs of extra metal that you're going to pour into the mold to account for shrinkage. Hot metals expand, cold metals shrink. The only common substance you're ever going to encounter that expands as it cools is water ice, right? So water, the density goes up and up and up, meaning it shrinks in volume until it freezes, and then it goes way up because it encapsulates air as it freezes and becomes a porous medium. That's an exception to this rule. But for all practical purposes, everything else that you're going to encounter as an average human being doing average human things is going to shrink as it cools, period. Okay? So you have to allow for this. There's three sorts of shrinkage that we have to think about as a metal cools. The first is your liquid state shrinkage. This is going from a really, really hot molten metal to a slightly cooler but not yet solid, still molten metal. That's low single digits, right? The solidification shrinkage is the largest shrinkage volume of the whole series. That's 5 to 10%, and these are very, very round ballparks. This will change a lot with every metal, and not just every base metal, but every alloy of every base metal is going to have slightly different shrinkage percentages. There are huge tomes that are just nothing but tables of data with this sort of stuff in it if you really need to get it precise. Okay? So this is the solidification shrinkage, is that moment where it goes from liquid to solid. It shrinks a lot in that moment. So it shrinks a little very slowly, and then it shrinks a whole lot all at once. Okay, that's important to recognize. And then pattern maker shrinkage. This is the shrinkage from being a hot solid to a cooler solid. Okay? We don't care about the pattern maker shrinkage when we're talking about our risers. We care about the liquid state and the solidification. Okay? If you need a pattern to be very, very precise, if you're doing this, if you're an engineer and you're casting things that are going to have to fit with other things and still move and do a job, you have to account for the pattern maker shrinkage when you design the pattern in the first place. Okay? If you're just doing what I'm doing and casting some little paperweights, meh, I don't care. This just means that my finished cast metal duck is going to be 1 to 2 millimeters shorter than my wooden duck. I don't care about that. It's irrelevant to me. But I still need to care about these a lot. And you deal with these at the mold making stage. So if we think about the simplest possible mold, where we have, I'm just going to draw the cope and drag here in yellow, because I don't want it to show up a lot.
That's not showing up at all.
Not showing up at all? Okay. I will draw the cope and drag in green, so it shows up at least a little. Cope, drag, okay? And then if we think about a simplest possible case where we have a sphere, that's the pattern, okay? Then our sprue is going to be a tapered cone. Everything has to be tapered when you're packing into sander. You can't get it out, okay? So your sprue needs to be a cone, not a sphere. And then we would cut gates to connect the base of the sprue to the pattern, okay? Simplest possible mold. And very little can go wrong with that because the sphere is the slowest to cool object possible. Okay? So you can, in a simple situation like this, basically think of the sprue as your riser, feeding a little bit of metal into there. It would need to be a little bit, I would want these closer together than in the drawing. Okay? But you can have a mold this simple if you have a set of shapes this simple, where the sprue is going to contain a little bit extra metal so that as this sphere shrinks, it can suck some metal down out of the sprue. And when you pour this, you can watch it go down the sprue and in. Okay? Because this will full first and start to cool before the sprue volume is filled, just because it was poured first. So as this cools, this will still be molten, and a little bit of that will suck in and account for the shrinkage. Okay? But let's say we have something a little bit more complicated. So I'm just going to draw another cope and drag here. I'm going to give myself a little bit more space. Now let's say my pattern is a dumbbell shape. I'll make that a little bigger. Okay, so there's my pattern. Now, let's say I do something like this, where I have a simple gate system here, and then I have a sprue coming up. Okay? Well, now what's going to happen? Well, this is going to fill with metal. This and this are going to cool slowly, but this is going to cool quickly. So if I just take this and I fill it from one end, yes, I can get it full of metal, but this is going to solidify, and this is going to solidify before these things do. So now what's going to happen is as this solidifies, it's going to shrink away from the edge of the mold, and you're going to get a lot of, either you'll get voids in the metal which then collapse in ragged torn edges, or you'll get usually the bottom being fairly solid and the top will be shrunken down and you'll have a really misshaped casting. Okay? Because this area filled before that. So we have to think about directional shrinkage. So what you would want to do when you're thinking about this layout, I'm going to draw this. I'm just going to draw this like if you were looking, this would be looking in from the side, right? Cope here, drag here. If I just draw this looking in from the top, okay, I'm postulating a dumbbell shape, so it's going to look about the same that way. So if I have, there's the middle of my dumbbell, there's the top, there's the other end, okay? What you're going to need to do is you're going to need, first off, you're going to need to fill into both of these, so you're going to need to put your sprue here, okay? Then you'll cut your gate this way. So that both of these fill before the middle does. That'll give them a little bit of a head start on cooling. And then we're going to cut another little gate system on the back end and then have another circular volume of liquid metal that can form over here. So as these start to solidify, they can suck liquid metal in from those extra reservoirs. That's what a riser is. Okay? Now, it doesn't have to be here. You can put this riser anywhere around there. You could, it actually probably would be a little bit more beneficial to cut the risers right here so that you would concentrate the heat. Heat source, heat source, heat source, heat source, heat source. And that way, these are going to lose heat slower and be able to fill in better. But you can put them either place. You could put risers on the ends if you want. Okay? When we look at something like the shape of the duct that we want to cast, if I just draw a very lackadaisical duck-ish object here, give it a little more belly. Okay, when we have something which is asymmetrical, put a little tail in there. Okay? And of course this would be top view because we're going to cast them on their side, right? Because that's where we have the bilateral symmetry. You always have to consider that when you're making a sand mold. What here is going to cool first?
The bill.
The bill and
The tail.
The tail, right? What's going to cool next?
The neck.
The head and the neck. And then the body's going to cool last. Okay? So this is good. You want to think about your directional shrinkage. Okay? And that's ideal. If you can get everything to shrink from the ends toward the middle, or vice versa, that will tell you where you need to have a riser system. So the bill is going to cool first, and it will cool before, let me draw this in blue, it will cool before the head and the neck do. Okay? So as the bill is cooling, it's going to suck metal out of the head and the neck. Okay? As the head and the neck cool, it's going to suck metal out of the body. So if I do something dumb and I have a sprue way down here and a very narrow gate system into here, I'm going to end up with a cooling cavity in here because there will be nowhere else to suck metal from. Okay? So, in the design of this mold, I will need to have a riser very close And then that would be the sprue. Or you could just put the sprue right in the middle of the riser and do it all in one thing. Okay? And that would look like, if I was going to look at the cross section of that, you'd have your pouring cup, your sprue tapering down. Okay, won't taper to a point. Okay, and then you would cut a riser as a large reservoir in the bottom of that sprue. Okay, so you need a riser here to feed metal into here. Otherwise, you're going to have crazy, stupid shrinkage somewhere in this area. Or, depending on, you might have like a big cut out of the neck there. If this is trying to draw metal that way and this is trying to draw metal that way, wherever those forces meet, you'll have a big shrunken area and a very ugly casting. Okay? So you have to put this riser in, but in a shape like this where you can accomplish directional shrinkage, you only need one riser instead of something like the dumbbell shape, which is going to force you to have two. So you have to think about these if you want a cavity of your mold, not just to fill, but to fill and stay full as it cools. And then the last thing that you have to think about are air vents. Sand is porous. It will allow some air to leave, but you still need to poke a wire or an ice pick through wherever you have a tall spot so that the air can leave as the molten metal is poured in. And remember, it's not just the air. You're using either green sand, which is water-bound, or Petrobond, which is oil-bound. Either way, you're going to get vaporized water or oil that's also trying to fill that cavity and force back out the sprue. So you need an air release vent. It doesn't need to be big, right? Air is very squishy. It will move around quite nicely. But you need to have a good way that that air can get up out of the mold. Okay? So there's a lot more to it than just getting your pattern with some sand packed around it. You have to think about all of these things. And for these ducks, this is how I'm going to do my riser design. Now the sizing of the risers is even more complicated than understanding what a riser is. And if you go online, look at technical manuals and ask how do you size your riser, they're going to consider both of these things. The riser needs to solidify slower than the pattern, and it has to have enough volume to feed back that 5 to 10%. Okay? So there are a whole set of mathematical formulas, and it's not hard math, it's straight up arithmetic. But the values you have to cool in it, have to feed into it, is you have to have a value for the insulation capacity of the mold, which you can look up for different mold materials. That's the least annoying one. And then you have to have a surface area to volume ratio. Okay? Which means you need to calculate the surface area of these complex forms and know the volume of those complex forms. The volume is easy. If you know the density of your pattern, you can put your pattern on a scale and calculate volume. Right? That's a simple density formula. Surface area is a lot more complicated. And these formulas are written for people that are designing patterns in a CAD program, where then the computer can do it for you. Right? The computer can take a point cloud around the outside of that CAD drawing, and it can either do a straightforward calculation, or it can do some calculus to figure out that surface area, and spit you out a surface area to volume ratio. And then the formulas are very easy to use. You as a hobbyist probably aren't starting with CAD. If you are doing something like Lost PLA, or your pattern was 3D printed, then you have a CAD model to work from. Go use those formulas. If not, consider two things. No matter where you are in these range, it's going to be less than 25% the volume of your original thing. Okay? And it needs to solidify slower than your pattern. Okay? So you can think about that, and you want your riser dimensions to be, it will fill after metal flows into the mold. Okay? So the mold has a head start on it. That's in your favor. Okay? If it has dimensions, which like the dimensions of the riser are at least as big as the maximum dimensions of the thing you're molding, and it fills later, it will cool slower. And then after considering that, you could just kind of logically figure, is it at least 1/4 of the volume? And if you meet those two criteria, you'll probably be fine. Now, if you're an engineer, what I just said is very cringy, and I recognize that. Okay? Because if you're an engineer and you're working to design molds for a professional foundry, you care very much about not having extra metal in this riser because it's wasteful of time and energy, and and if the foundry is throwing this away and selling it for scrap weight and not remelting it, then it's wasted material. So you're trying to get the absolute smallest riser that will still work. Okay? If you're a hobbyist, you're going to take all of this schmutz that stayed outside the mold and just remelt it when you make your next duck. You don't care. And the guidelines I just gave you are very much overkill. So you will need extra metal to go into this riser to make sure your mold fills full. If this is at least 25% and at least as big as the maximum dimensions of your mold, it should work. You might have a bad casting and say, oh, I still had an air void, I'll make it a little bigger next time. Totally legitimate. You're a hobbyist, you can afford to do that. You're not in a time is money situation. So that's why I'm giving you a time is not money rule of thumb for thinking about your riser. But if you are using a 3D printed model and you have the CAD access, you can calculate that surface area to volume ratio and then go look up those formulas, and they'll work for you, and you can get a much more precise estimate of how big your riser should be. But no matter how you cut it, you need a riser to get a successful casting. So thank you very much for bearing with me for this little bit of technical information. You need to know this in order to make good castings and good molds. Okay? It's not something you can skip, and skipping it leads to untold problems for many, many hobbyists. Okay? So thank you so much for sticking with me. I hope it helped you. If it did, I would be most grateful if you gave it a thumbs up, because the YouTube algorithm loves that and it helps it know to show this video to other folks. So I'm always grateful when you do that. Thank you. And while this, I know, is not as exciting and riveting as actually, doing things, we're in the middle of doing things. You saw the flask be made recently. We're going to go into making pattern boards and setting up our actual molds. And now you know why the things on the pattern board are there. So I hope that you will continue to follow along with this little project, and I'll see you next time here at Old Ways Rising.